Ever wondered how AI systems actually learn? It's not magic, it's a complex interplay of mathematics, algorithms, and data. Today, we're diving deep into the mechanics of neural networks, the backbone of modern AI. If you've ever wanted to understand how these systems process information at a fundamental level, this is the video for you. Let's start with the basics. A neural network is modeled after the human brain, but it's far from a biological copy. At its core, it's a mathematical structure composed of layers: input, hidden, and output. Each layer contains nodes, or neurons, which perform calculations. But here's the kicker: these neurons don't just do simple math. They apply something called an activation function, which introduces nonlinearity. This allows the network to model complex patterns, like recognizing a cat in a photo or translating languages. But how exactly do these networks improve over time? The answer lies in a process called backpropagation. Imagine you're teaching a child to ride a bike. You correct their balance, adjust their posture, and gradually let them go. Backpropagation works similarly. When a neural network makes a prediction, it compares the result to the correct answer using a loss function, essentially, a measure of error. Then it propagates this error backward through the network, adjusting the weights of each connection using gradient descent. This iterative process minimizes the loss, refining the model's accuracy. But here's where it gets technical. The gradients are calculated using the chain rule from calculus, enabling precise weight updates. Now let's talk about the unsung hero of neural networks, the activation function. Without activation functions, neural networks would be nothing more than linear regression models. These functions introduce nonlinearity, allowing the network to learn complex mappings. Common examples include ReLU, which outputs the input directly if it's positive, otherwise zero, and the sigmoid function, which squashes inputs into a range between 0 and 1. But why does this matter? Think of it as the decision-making layer. For instance, in a medical diagnosis model, the activation function helps determine whether a tumor is malignant based on input data. However, even the most advanced neural networks face challenges, particularly with data and computation. One major hurdle is overfitting, where a model memorizes training data instead of learning generalizable patterns. Techniques like dropout regularization randomly deactivate neurons during training, forcing the network to distribute learning across multiple features. Another challenge is computational cost. Here, architectures like convolutional neural networks, CNNs, optimize processing by leveraging spatial hierarchies, while transformers use self-attention mechanisms to handle sequential data more efficiently. These innovations are pushing the boundaries of what's possible. Neural networks are more than just a buzzword, they're a revolutionary tool reshaping industries. By understanding their inner workings, you gain insight into the future of technology. If you're curious to explore specific architectures or dive into code examples, hit the subscribe button and let me know in the comments. Thanks for watching, and remember, the next breakthrough in AI could be just a few equations away.